great welcome to the series on Abaqus. So here we'll discuss part B of tutorial 12, which discusses the application of Abaqus in the analysis of a structural bracket. The problem statement is already detailed in part A, and hence it will not be repeated here. So in this part, we'll discuss about the modules assembly step interaction. So let us start developing these modules for the structural bracket that we have already developed in part A. So let us visit Abaqus. So let us proceed to the assembly module. So we'll start creating the instance of the different parts. So we'll start with a column. It's okay. As you can see that the column need to be rotated about the x-axis to make it vertical. So let us rotate this instance. So select the instance. Done. So we have to rotate about the x-axis. So I will mention any value on the x-axis to define the x-axis. Okay, and this is okay, fine. So this means that this position is acceptable to us. So you can see that yes, the column is rightly positioned. Now let us create the instance of the flange portion of the bracket. Okay, so you can see that okay. So now for the convenience, let us just translate along the z-axis. So I will select this instance. Okay, fine, done. So let me just translate it by say around say another 400. This is just for convenience, nothing else. Okay, fine. So this is okay. Now we shall apply two constraints, like the coaxial constraint and the facial constraints, to bring the plate in the right location. So let us first proceed for the coaxial constraint. Okay. So let us select the two cylindrical surfaces. This one for the mobile and this one for the fixed, and check the normal direction, it is acceptable to us. Okay, so you have seen that they are made coaxial. Now let us apply the face-to-face constraint. Okay, fine. So we will select the planar surface. This one is okay, and this surface is also okay, and the normals are in the same direction. Okay, and obviously this distance should be the thickness of the plate, and the thickness of the plate we know it is 16 mm. Okay, so yes, so you can say that yes, it is rightly placed. Okay, this is the flange plate for the bracket, and let us just rotate it a little bit. Yes, you can see that all the holes are coaxial and it is rightly placed. And so let us start making the instance of the bolt. Okay, okay, fine. So just as in the previous case, let's just translate this bolt. Done. Okay, and we shall translate it along the z-axis. So use say for example say 500 is okay for me. 500, this is okay, so that I will be able to easily handle all operations concerned to the bolt. So just like the other case, we need to apply again two constraints, like the coaxial constraint first. So let us apply it. So this is my coaxial constraint. So select the two cylindrical surfaces. This is a one, and this is a second. So let us see the normal directions, whether they are acceptable. They are opposite, so we have to flip it. Okay, fine. So they are now coaxial. Now let us use the face-to-face constraint. Okay, fine. So we'll select the two planar surfaces. So this one and this. Okay, the normals are in the same direction, acceptable to us. And this distance should be the head thickness, right? So that's a 15 mm. That's okay. So look here. So the bolt is rightly placed. You can also see the other side, whether it is properly sized, whether it is properly placed or not. Yes, you can see that yes, it is rightly placed. There is no issue at all. So let us go for the linear copying of these bolts. So we shall go for the linear pattern. and select the instance, and here we have got only the bolt. Okay, select it, done. And in one direction we have this 130 mm, and the other direction we have 3, and with the spacing of say 150 mm, 50 mm, and this is this direction it is applicable to us. No flipping is required. Okay, so you can see that yes, all the bolts are properly placed. There is no issue at all. So let's just rotate it and see both sides. Yes, this side is correctly placed. There's no issue. Let us see also the other side. Here also we don't have an issue. This side also we don't have an issue. So now let us start making the instance of the web plate of the bracket and correctly position it. So create the instance. Okay, so we have the web bracket. Okay, fine. So okay, so now let us again translate it as usual. So translate the instance. Okay, select it. Okay, fine, done. And I would like to translate along the z-axis. So do it by say 500 mm. Okay, that's okay for me. Now obviously you know that this position is not acceptable to us. It need to be rotated, okay, about the y-axis by 90 degrees. So let us do that first. So rotate the instance. So select the instance. This is the instance. Okay, fine, done. And we need to rotate it about the y-axis. So let us change this to some point on y-axis. Okay, and this rotation we need to keep it as a -90, -90. Okay, so yes, so yeah, now you can say that this is acceptable to us. This orientation is acceptable to us. So now let us translate the entire instance. That will be the best way. So translate the instance. Okay, so we will select this instance to be selected, done, and the starting point. We have to select it properly. Okay, I will select the midpoint. This midpoint I will select. Okay, and the end point. This point should correspond to this point. Okay, yes, so this position is acceptable to us. Okay, fine. So this means that the assembly is correctly, the final required assembly is correctly, okay, developed. One very important thing to be noted here is that we don't have any connectivity between the web plate and the flange plate, and these two components need to be tied properly, and this we can manage during the interaction module. So having completed the assembly module, let us go to the next module, that is step. So we shall obviously start a new step. So step of BKT, and that will be placed after the default initial one, and the analysis type will be the static general. So continue, and in this case obviously we are interested in the nonlinear behavior as well, so keep NL geom as on, and as it is a nonlinear geometry problem, we expect some convergence issues. So let us proceed for atomic stabilization using this option. Okay, fine. Now coming to the incrementation, let us keep the maximum number of increments slightly higher, and the minimum, because there could be a convergence issue, so let us keep this as a very small number. So we would like to keep it as a -15. Okay, and we'll ask Abaqus to start with the 0.05 and to have the maximum increment as 0.1. So that's all regarding the step module. Now let us proceed for the interaction, but before the interaction, we would also like to have the definition of some of the field outputs. So let me call it as field output BKT. Okay, continue. So let us start selecting the required stresses. Among stresses, I will select the 1/6 stress as well as its components, and that's okay. And now regarding the displacements, I'll select the U translations and rotations, that's okay. And now this is basically was a bolt interaction is also there. So we would like to have the section forces also, because we would like to see the forces in the bolts at each time increment. That's okay. And now finally going to the contact, we would like to have the contact stresses also written to our output. So that's okay. So these are the variables to be written into our ODB. That's the output database file by Abaqus. That's okay. Okay, fine. Now we can straight away go for the interaction. So in the interaction, as usual, we have two jobs. One is we need to define the interaction property. So let us define test interaction property, for example, the BKT, and it's a contact type. Continue, and we need to define two properties. One in the tangential direction. In the tangential direction, as usual, we shall go for a penalty function with a friction of 0.30, and next we shall go for the normal behavior. We'll go for a hard contact, and ensure that you check this label, that is allow separation after contact, because this will be very much useful for this type of problems. So this is okay. So this means that we have defined the interaction property that is expected between the surfaces for this tutorial. Now, to define the contact pairs, we have many options left. We can go for a general contact, we can go for a surface to surface contact, but selecting each surface manually is a very Herculean task. So it is better that you make use of the already the standard procedure, that's a find contact pairs, automatic okay, location of the contact pairs by Abaqus. So just press this button. Okay, fine. So I would like to find all the contact pairs that is separated for just for example one. So let me see how many contact pairs I have. Okay, so yes. So as you can see that yes, Abaqus has told me there are almost 26 okay, contact pairs available to us, and each of these contacts or contact pairs are listed here. You can examine each one of them. Okay, so before that, what you can do is you can just enlarge it a little bit. So just to highlight some of the contact pairs that is that is highlighted by Abaqus. So you can just press, for example, column to bracket flange, what it is all about. Yes, it is says the contact between the column and the bracket flange, these two. So this surface space are being highlighted over here. On the other hand, for example, if you talk about the column and the bolt, look here, the column and bolt here, it is highlighted here. Let me just zoom it. As you can see that this is nothing but it's a contact pair between the head of the bolt and the column. So you can easily identify each one of this. And for example, if you are talking about this one, you can see that yes, it is basically is a contact pair between the bolt and the column. That is the inward element is the shank of the bolt. So that way you can identify each one of this, and if you find that some of the pairs that is highlighted by Abaqus is not relevant, you can delete it also. And here we can use one more facility available here. Abaqus shows the type of interaction. Okay, so here, as I told you, we need to connect the web as well as the flange of the bracket component. So this can be done easily here. For example, if you go to the last contact pair highlighted by Abaqus, you can see that yes, this is nothing but it is the bracket flange and the bracket web. So this is truly highlighted over here. So now what we need to do is that here we can go to in the interaction, we can select not the interaction, basically these are tied together. We don't expect any kind of interaction here, just tie it, and here it is basically we want not a surface to surface, but we want a node to surface interaction. So that is okay for us. So here we made use of the automatic detection of the contact pairs by the Abaqus, and also we have defined the tie interaction between the web and the flange of the bracket properly. So now this is okay. So you can see that yes, Abaqus has indicated some kind of a rectangles over this face, indicating that these two components are being properly tied. So that's all about the interaction module. Now we can proceed to the next module, that is a load module. So let us proceed to the next module, that is a load. So here we need to apply both the boundary conditions as well as the load. let us first proceed for creating the boundary conditions. So before applying the boundary conditions and also the loads, we would like to establish some reference points through which we will apply the loads as well as the boundary conditions. So we'll go back to the interaction so that we'll be able to establish the reference points. So we'll establish three reference points. A reference point 1 at the CG of the bottom cross section of the column, and reference point RP2 at the top, and the reference point RP3 at the CG of the load applied phase. Okay, so let us first proceed for obtaining the coordinates. So first we shall go for creating RP. Let us find out what will be the coordinate. So we shall just rotate this a little bit so that we'll be able to see this phase. Okay, fine. Now we can obtain a query, the tools with the query, and we would like to find out the coordinates. So let us select these 2 points and find out what exactly are their coordinates. Yes, so done. So this means that we have got minus 3.75, minus 1500, 0, and 3.75, minus 1500, 0, which means that the CG of this center will correspond to 0. We have to find out the average. 0, minus 1500, and 0, right? So let us start having the reference point RP1, and as we know it will be 0, 0, comma, minus 1500, 0. So okay, fine. 0, comma, minus 1500, comma, 0. Okay, fine. So you can see that here's RP1. It is exactly placed at the CG of the bottom section. So in a similar way, we can also obtain the coordinates corresponding to RP2 and RP3. So that's already pre-calculated. So let us just feed it into the Abaqus. So we shall now create RP2 at the CG of the cross section. So create. So let us enter the coordinate. This will be obviously, it's on the top. So on the top we have got the coordinate as 0, 0, 0, 0, comma, 0, comma, 0. So yes, you can say that yes, RP2 is now exactly placed at the CG of the cross section. The pre-calculated distance, and it works out to be, the coordinate works out to be 0, 0, 0. Now similarly, we need to place the RP3, and this RP3 will be placed at the CG of this cross section. Okay, and this pre-calculated distances works out are already calculated. So we need to calculate the corresponding coordinates and then feed it. Okay, so press it again. So for the RP3, calculated coordinate works out to be 0.005, comma, then we have got minus 600, then comma 425. So you can say that yes, RP3 is placed at the CG of this section. So we have established now these 3 reference points through which we'll apply the loads as well as the boundary conditions. So before applying the boundary conditions, let us tie the reference points RP1, RP2, and RP3 to their respective cross sections. This will be done through the constraint command operation. So let us define the constraint for RP1, okay, and we'll choose the type as coupling. Continue. So now let us select the reference points, that is RP1. Done. Now let us go for selecting the surfaces. Okay, so done. So now we would like to have all the degrees of freedom being constrained. So this is okay for us. You can say that yes. Now the RP1 is tied to the cross sections. So let us do the similar exercise for the RP2 and RP3. So first we shall go for creating the constraint for RP2. Okay, so let's create the reference point RP2 constraint. So we'll call it as constraint RP2. RP2. Okay, that's good enough. The type will be the same. So continue. So let us select the constraint point. My constraint point. Done. And select the surface. So let us start selecting the surfaces. Okay, so done. So that's okay for us. You can say that yes, RP2 constraint is also created. Now let us proceed for creating the constraint for RP3. So constraint RP3, RP3, okay, fine. RP3, it's okay. So select the constraint control point RP3, done. The surface, here the surface is very simple, is this surface, okay, done. Okay, you can say that yes. So the constraint is provided for RP3 also. Now we are ready to apply the loads and the boundary conditions. Proceed back to the load module. So let's start creating the new boundary conditions. So let me have BC, for example, I'll call it as BC bottom. That's a pin condition. So it will be created in the initial time step. Okay, and as a displacement is continue, and we have to select the region. So instead of selecting the region, now we have, as we have already tied the reference points, we have to select only the reference points RP1. So done. Okay, and we will restrain U1, U2, and U3 because it corresponds to the pendant. Okay, so fine. So now let us proceed for creating another boundary conditions. So create. So we can say that it is BC. Let me say that is a top, and the displacement will be again the same. So we have to select the node point, that is my RP2. So select it. Okay, so done. So here again we'll pin the ends U1, U2, U3. That's okay for me. Fine. Now we need to create one more boundary conditions for the bracket, because during the loading we expect that the bracket is likely to buckle, right? So in order to prevent the buckling or the out of plane movement of this bracket, we would like to restrain this entire plate surface against the translation in the x direction. So let us create one more boundary condition. So we'll call it as BC, we'll call it as a BKT, that's for the bracket. So continue. So here we need to select the regions for the boundary conditions. So this center surface, okay, so done. And we want to restrain the movement in the x direction, so we need to restrain only U1. So that is okay. So fine. Okay, now we have applied all the boundary conditions. Now we can apply the load directly at the point RP3. So let us create a load condition. So we'll call it as the load BKT. Load BKT, okay, fine. And this should be applied in an analysis step of BKT. And this is essentially a concentrated load as already stated in the problem statement. So concentrated force, and it should be applied on the reference point RP3. Done. So it will be applied in the y direction, that is the CF2, and we have to apply it as a minus 200,000. So it's 200,000, which indicates that it is the load applied is 200 kilonewton, and if we applied in a monotonous way, that's why we have selected amplitude variation as ramp. So that is okay for us. So you can see that yes, the load is applied at the reference point RP3 as indicated over here. So having applied the loads and the boundary conditions, now we are ready to proceed to the next modules, that is a mesh, job and visualization, which will be done in the part C of this tutorial. Till then, bye.